Okay. Hello, everybody. I assume you can all hear me pretty well because I can hear myself echoing off of the walls. So hopefully I'm not too loud. Sometimes I get a little bit excited and I kind of shout a little bit. If I'm shouting and it hurts your ears, please let me know. Don't be afraid to stop me in the middle of what I'm saying because I don't want to hurt your ears. So with that in mind, my name's Philip Carter. I work on the .NET compiler and tools team at Microsoft. And my focus areas are F#, kind of the whole thing, C# compilers, and .NET tooling integration inside of Visual Studio. But I'm here to talk mostly about F# today. So I called this talk, Why You Should Learn F# this year, but I feel like I should have maybe called this talk, Why You Should Learn Functional Programming this year, and hopefully use F# as your way to learn functional programming. And that's because F#, although it's a fantastic language, like the fact that it's F# isn't really as interesting as the fact that it's a functional programming language. And I think functional programming is something that everybody should be learning, especially now. And so there's no better time to start than, well, pretty much right after this talk. So first I want to just briefly say like why functional programming, then briefly say like why F#, and then I want to get into a little bit of with F# and Jupyter Notebooks, which is some new tooling for F# that we're going to show that we just released, actually, I think, yesterday in a public preview form. So, why functional programming? Well, functional programming is, I like to think of it as sort of like an emerging mainstream today. It's actually, FP has been around for a lot longer than object-oriented programming. If those of you who are familiar with things like the Church-Turing thesis, or the lambda calculus, or these things that were all invented between the 1930s and the 1950s, but they haven't really found their niche in modern programming until fairly recently. React.js, probably the most popular JavaScript framework out there today, or I think they like to be called a library, not a framework, sorry. That is like basically all about functional programming. Spark, similarly, is like at its core about functional programming. Machine learning, especially optimization and especially next-gen, machine learning is rooted in functional programming and actually incurs a functional style in the languages that you use. And modern programming languages are also adding functional programming language features because they're finding that these sorts of features help developers when they're building modern things. So there's a lot more examples of where it's sort of an emerging mainstream. I just wanted to give you a few short ones so that they're easy for you to keep in mind. So React. One of the reasons why React is functional, it's all about a declarative programming model, right? You don't imperatively define UIs. You declare these composable UI components that you sort of piece together, and you put together sort of this like functional pipeline of UI that sort of changes based off of inputs that you get. This component-based sort of UI like piecing together has made it extremely popular because it's super easy to reuse components pretty much anywhere inside of your application. And immutability is also preferred when you're doing React programming. So I grabbed a snippet actually from their introduction. It says the main benefit of immutability is that it helps you build pure components in React. Immutable data can determine if changes have been made, which helps to determine when a component requires re-rendering. It's basically a fancy way of saying if you do things with immutable data inside of React, React just runs a lot better. And that's like, they built it around that entire concept. Apache Spark, also if you're doing any kind of big data processing. If you've used it before, you're probably familiar with the fact that it's all about declarative programming. Similarly, the core concepts themselves are immutable, and that's because they don't want to encourage the notion of being able to change things in place when things might be executing sort of in arbitrary machines anywhere across the world. Like you can't rationalize that sort of complex environment with in-place state changes. So that's why they make things immutable. And as I said before, functional composition is sort of at the key of functional programming, and this is what Apache Spark also does. And when you combine that, you get really awesome ways to transform data that you can't really do with imperative programming. And so this is actually a code snippet like directly from their homepage. And I don't know if you're familiar with the concept of a flat map or a reduce. These are like rooted within functional programming. This is the very first code sample that you'll ever see if you're going to try to use Apache Spark, and it is functional programming. It may not necessarily look like totally alien or anything like that. Well, I don't know. There's the underscore plus underscore thing, but that's That's Scala. They also have a Python version. And the Python version, it's the exact same thing. They have flat map, they have map, they have reduce by. They try to encourage this style of programming. And then with machine learning, it's very new, somewhat immature space, but things are already evolving quite a bit. Two next-gen machine learning systems are what are called JAX and Swift for TensorFlow that are being invested in very heavily right now. These things have what's called automatic differentiation at the core of their engines. This is sort of like the magic behind machine learning. It's basically just math. It's not really magic. It's just a higher order differentiation that goes on. And if you've taken a calculus course, you're familiar with the notion of differentiating things is effectively like taking functions of functions and composing these functions together. That is functional programming, and they actually encourage a functional style. If you go to the documentation page for JAX, which is sort of this framework / extension to Python for enabling machine learning research that Google have been trying to invest in because TensorFlow has not been suitable for some of their needs. They literally say it right there, do use functional programming, use these built-in functions, construct new arrays instead of mutating in place of ones. And then they have this big old list of things that you shouldn't do that are actually defaults in the Python programming language. So they basically say, hey, take this part of the language that you can use for functional programming really nicely, and use only that, please, and our system will work a lot better. So it's sort of kind of heading in that direction. For those of you who are familiar with C#, modern C# is also functional. Link, I guess, I don't know, came out in like what, 2005, 2008, may not necessarily be modern in these days, but certainly like most C# programmers that are doing modern C# development are using link all over the place. Similarly, async has its roots in functional programming where you want to take the context of execution, say like asynchronous execution, and lift it into the type system and enforce that at the type system level. Nullable reference types are inspired directly from functional programming languages that do not allow null values by default in their code. Patterns and being able to match over those patterns is, again, comes from functional programming. Local functions are functions that you can embed inside of methods in C#. Embedding functions within functions is a functional programming concept. And expression-bodied members are a way to not have to have this block body and explicit return. You can just have an expression be the body of a method or a property. And that's just what it is. Again, that sort of brevity, that sort of way to just sort of say, hey, I'm dealing with expressions, not necessarily statements, is functional programming. So there's sort of this emerging trend that's going on. Languages are adopting this sort of stuff. JavaScript is also adopting this sort of stuff. And in fact, you could argue that JavaScript has been kind of functional in a way since its very beginning because it has what are called higher order functions. Higher order functions are functions that can be treated as values. They could be say, oh, I declare this function is a value, I can pass it around. I can pass a function to another function, I can return a function from another function. JavaScript has allowed this from day one. They extended this with arrow functions and async and promises to be able to lift more functional programming into the type system. They are introducing, actually I think async is the one that's being introduced here pretty soon. That was inspired from a variety of languages that adopted async that came from functional programming. So I don't really know why this is happening. I mean, as a fan of functional programming, I think I could come up with reasons why, but I don't think I can objectively tell you, yes, this is why functional programming is happening. But it seems to be happening. And it seems to be happening when people are building modern stuff with the cloud, with larger data sets, and when they're doing machine learning. It seems to be at least coincidental. So this is sort of a trend. Now, thus far, I've not talked about F#. I've not mentioned a single other functional programming language. In fact, I've mentioned C# and JavaScript, which most people don't think as functional programming languages. Well, that's the sort of thing that, while you can certainly do functional programming in these languages, they weren't necessarily built for it from the beginning. And so if you're interested in learning functional programming, you want to really understand the concepts and you want to have a language that understands those concepts built in, it's good to pick a functional language like F#. So that's why I think you should learn F# this year. Not necessarily as a replacement for C# or replacement for anything like that, just as a tool for learning functional programming so that you can hop onto this sort of trend that seems to be happening. And one of the reasons why you should learn it is functional programming is first class. We have immutability by default, right? This immutability thing that I talked about. It's not something you have to opt into, it's what you get by default. We're declarative in terms of the way that you program things in F# by default. functions are first class. There's a functional standard library. And we have a lot of powerful types in the language that enable you to very succinctly model things and then pattern match over those data types so that you can get going. It's also first class on .NET. And I think that really matters if you want to learn functional programming, because typically, like, your first thing that you're going to do in a new language is usually going to be like a little baby application or something that, doesn't really do much because you just kind of want to get your head around the syntax. But after that, if you're interested in going further, you're likely going to want to build some kind of project. And that's where integration into .NET matters, because we have full support on .NET Core. We have full access to the entire .NET ecosystem with like the NuGet packages, pretty much any sort of standard SDK for a platform that you may want to choose to integrate with. And we have really good tooling that's ubiquitous, right? We have VS tooling, and VS 2019 just comes installed by default. You can use it in Visual Studio Code with .NET Core. And we have some preview Jupyter Notebook support that I'll show you a little bit later. So, actually, this is a slightly outdated deck. First, I'm going to show you something different from F# on Jupyter Notebooks. So, here is the F# homepage. You can go here at aka.ms/F# home. I'll have a link to that at the end. And there's a big old button here that says Get Started with F#, and I imagine you know what that will do. When you do that, that will force you to download .NET Core, because .NET Core is where F# comes by default. So if I were to go .NET new console-lang F#, right there, that would create a brand new F# console app. I'm not going to go through the pains of showing you how to do that right now. I already have this all built out. So briefly going through some of this code. I hope all of you can see this. I tried to bump up the font pretty large here. Here, I'm just opening the system namespace. This is just like a using declaration. And I'm defining a couple of types. I mentioned these types earlier, lightweight data types. I have a square. A square has a side. A rectangle has a length and a width. And a circle has a radius. You can see that in the tooltips as well if you prefer to not necessarily read the code. This is sort of my domain. I'm just briefly representing 3 different kinds of shapes. Now, if I have 3 different kinds of shapes, presumably I'm going to want to do something with each of those kinds. The way that I would represent a bit more of a generic shape type would be a discriminated union, or a union type. I have a square, a rectangle, and a circle. And I also have an undefined shape, because I may want to have a program where somebody could say, hey, I want to do something with one of these shapes, but they don't specify a square, a rectangle, or a square. Or a circle. How do I represent that in my code? The answer is I just have effectively a little case right here that just says undefined. And this is pretty nice, because I can write code that's very symmetrical to the type definition. Here I say a shape is either a square, a rectangle, a circle, or undefined. And then I have a function that I declared called getArea. It takes in a thing called a shape. The shape is actually using type inference from the F# compiler to infer that it is one of these types. And then I'm going to pattern match on the shape of the shape. And in this case, it's defined almost identically to the type declaration itself. I have a square, a rectangle, a circle, and undefined. If I want to get the area of a square, I just multiply the side by itself. If I want to get a rectangle, I multiply the length by the width. If I want a circle, I go 2πr, or 2 times math.pi times c.radius. And then if I'm undefined, I'm just going to say I got 0, right? If I didn't get any of these 3 things, I have no area. That's probably pretty reasonable. So then I'm going to have another function that uses pattern matching again, except not on the shape type. I've actually named this shape, but it's of type string. This is because this is going to represent user input. And so user input is basically a string when it comes from a program. You have to convert it into an actual type to be able to make use out of it. So I'm just going to use the .NET method to lower the string, so that whatever they give me, it's going to end up looking like square, rectangle, circle, or this little underbar thing. This means literally anything else. They could have typed absolute garbage at the command line. It doesn't matter, because I will just say that that's an undefined shape because I didn't define some arbitrary thing. So we're just going to go with that. So again, it's still somewhat symmetrical to everything that I defined before. And then at the very end, I have a program that actually accepts user input. Taking a main function, takes an argv, checks to see if there's nothing in it. If there's nothing in it, we just exit. And then for each of the shape strings inside of argv, which is a string array, I'm going to get the area. And I do that with some function composition. Notice that I'm not mutating anything in place, because I don't need to. This is functional programming. So I take this shape, which is a string, and I pipe it. This is the pipe operator. This is just like passing it as a as a parameter, which I could also do, but this sort of lets you stack function calls on top of each other rather than have nested function calls that can sometimes be a little bit harder to read. And I'm saying the shape is the input to the string to shape function, which we defined right up here, and then the output of string to shape is going to be the input to the get area function, which again was also defined there. And then for each of those, once I actually get the area, which now you can see the compiler has inferred to be type float rather than a string, I'm going to just print that out. So I'm in VS Code using the F# plugin here, and I'm just going to .NET run. We'll go square, circle, rectangle. So this is going to recompile this on my machine, and it should run it here pretty soon. There we go. So we saw that a sample area of a square is 4, so because we defined that square to have a side of 4, the circle is 12.6, and the rectangle is 8.0. And if you did, you can probably double check my math here, but I imagine it's probably correct. So this is pretty cool. This is like a little toy program, honestly, but this is the sort of thing that you can use to get your feet wet first. Another way that you can get your feet wet, if you don't knock your mic out of your pants, let's see here. Another way that you can get your feet wet is using Jupyter Notebooks, which is this is sort of the preferred tool for data scientists and people who are doing exploratory data analysis. So I installed Jupyter Notebooks on my machine here, and I'm going to run this command called Jupyter Lab. This is going to run an in-browser IDE, where I have full F# support here. So you see this indicator at the top right, this little circle, that says that there's a kernel that's busy. This is basically a process that hosts the F# compiler, and it's able to take user input and then produce output in a really nice way. So defining some quick basics here. So now you see the kernel is not, that little indicator is now circled. That means it's finished initializing. So I can just get inside of one of these cells here, and I can just execute code. And this is a fancy way of printing out 42. It's just basic arithmetic. That's pretty cool, but when you're doing exploratory stuff, sometimes, or any kind of data manipulation, you might want to generate data programmatically. A way to do this is with range syntax. I just have a little bracket there, and then I go 0.10. That just says from 0 to 10, and then I just take numbers and I print that out. And so there's a little nice tabular data right here. So I got from 0 to 10. These were my numbers. Now, if I want to take only a subset of that, I can basically use that same syntax, but I put a little dot in front of that. That is a slice. Again, this isn't manipulating numbers, right? So if I were to do this, you'll see that numbers is still there. I've actually produced a new list here that's just representative from the second to the 5th index. And then I can just take a single value there. So I showed you how to define some functions before. I want to show you something a little bit more interesting. So here's a function that takes a square, just takes a value, multiplies it by itself. Pretty straightforward. I'm taking the square of 12 by just calling square 12. Now I can map this function onto numbers. This is a functional programming concept, taking a mapping. A map is a function that takes a function as input called a mapping function, and it takes in a set of things to call that function on, and then it produces a new output based off of that. So now it's their squares, 0, 1, 4, 9, 16, 25, so forth, all the way up to 100. Now, what I'm going to show here is a wonderful F# plotting library. We actually use this in the C# kernel too because it's that good. So I'm just going to take those same squares, and I'm going to draw a line chart off of that. So you can see this is a graphical representation of the same numbers that we have, all embedded into the same notebook. So that's pretty cool, but let's just kind of look at how the data relates to the mapped data here, right? Just scrolling up here really briefly, I opened up this namespace, open xplot.plotly. I defined a thing called squares, where I take my numbers and I map square over that. In fact, I think I didn't define that up there, so I had to actually define a name. And then I pipe that into a function called chart.line. That comes from the library itself. This library is actually a NuGet package that we just have installed inside of this notebook environment here. So let's say I want to take the original numbers and I want to take the squares and I want to plot them both in the same graph. How would I do that so I could see their relationship to each other? Well, I define what's called a series. I'm going to do a scatter series. This is just sort of like some dots on a graph, if you will. And the x value is going to be the original numbers, and the y value is going to be the numbers, right? From 0 to 10, and then the y is going to be effectively the series, 0 to 10. It's basically just a list right here. And then squares, which we defined earlier, is just the squares of those. And that's going to be in the quadratic series that I defined there. Then I'm just going to combine the number series and the quadratic series into a list. This, again, this sort of combination of just these little components that I define here, this is at the core of functional programming, and it just works. And that's because there isn't, a whole lot of magic going on in this charting library. This charting library just takes effectively a sequence of values. And all I've done is combine two sequences and produced a new sequence out of that. And so it says, oh, well, you have these two sequences. You have a sequence that has two sequences on it. So I'm going to go through that sequence, and I'm going to process each of those two sequences that you put inside of there. And it's very, very succinct to do this sort of thing. And then you can see, a graphical representation of the values that were actually produced there. This is a very compelling sort of thing for data scientists, non-programmers, the sorts of folks who are technical but didn't necessarily get a computer science background, but they're really good with numbers, they're good with math, they have a lot of domain expertise, and they want to be a part of software development. Especially if they haven't learned things like object-oriented programming or something like that. It can be challenging for them to come to a language like C# or Java or something like that, where there's a whole lot of conceptual overload just to sort of get your basic hello world going. In functional programming, do we sort of elide all of that stuff and just say, it's just values and functions? And that's sort of a little lie, because these languages are rather large. There's all sorts of little things you can do. But for the purposes of being able to generate some data and look at the representation behind them, all I did was just have some values and some functions. And those functions just process the values. And I was able to do that inside of Visual Studio Code and inside of Jupyter Notebooks here. I don't have time to show you the Visual Studio integration, but you should be able to check that out if you have Visual Studio 2019 on your machine. So that just about wraps that up. So one small call to action here is just to get started if you don't have it on your machine already. If you go to aka.ms/f#home, that will take you to that original page that had that big button that said get started on it. And I recommend you just go there, try it out in whatever environment you like, and see if you could produce a little program that takes strings as input and produces shapes. Or maybe if you're feeling particularly up for a challenge, you could spin up a Jupyter Notebooks environment with .NET, and you could go ahead and start plotting sorts of simple data like what I just showed you right there. We actually have a whole lot of examples about how to do this sort of stuff in notebooks if you're interested in doing this further. So, thank you very much.